This lecture is going to focus on electron treatments, percent depth doses, and isodose lines. What I have here is just a flat water phantom. The entire phantom is just filled with the density overridden to water. I have 5 different electron beams. You can see at the bottom of the screen here, fields 1, 2, 3, 4, and 5, each with a different electron energy, 6E, 9E, 12E, 16E, and 20E. They're all set to a standard SSD of 100 centimeters, and they each have a 15 by 15 cone. Since at Gunderson, that's how we normalize our electron fields, is to a 15 by 15 field size. What I've done is drawn a profile down the central axis of the field from the surface to roughly 20 centimeters. That resulting profile line gives me something that looks like this. And then what I'm going to do is I'm just going to step through each of the different electron energies and try and discuss some of the concepts of the percent depth dose curve as well as the isodose line as it pertains to your soft chalk lectures. Keep in mind that electron fields vary depending on linear accelerator manufacturer and even treatment machines, because it depends on the accelerating waveguide. It also depends on the scattering foils and anything else that the electron beam is going to interact with before hitting the patient. So they'll be relatively universal in a broad sense, but if you want specifics, you're going to have to go to your individual departments. So let's start off with 6E. I have a 6E field, 100 centimeter SSD, 15 by 15 cone, and I've given just 100 monitor units. And all the isodose lines are in percentages. If I zoom in, we can see that in the upper left-hand corner, 100% isn't shown. Since I have 100 monitor units, I should have a relative point for D max. Cyan color is 95, the yellow color is 90, orange is 80, and then magenta is 50, and white is 30. If I were to blow up the percent depth dose curve a little bit, my surface dose for 6E, 78%. So I think in the soft chalk lecture I kind of give you a general rule of 75%, and then the electrons roughly went up 5% per beam energy. So 75 for 6E, 80 for 9E, 85 for 12E, 90 for 16E, and 95 for 20E. And those are general rules. So my surface dose is located at the phantom surface, and then I increase to D max, which for my 6E beam is 1.2, and then I decrease down to D90 is going to be the depth of 90% isodose line, 1.6. So you can see from 1.2 to 1.6 in 4 millimeters I've lost 10% of the dose. Now I go down to D80, and my depth is 1.8. So the electron fall off is incredibly fast for low energy electron fields. So from 90% of the dose to 80% of the dose, it's only taken me 2 millimeters. So D90 is typically where we prescribe electron treatments at, the depth of 90% isodose line. So that's at 1.6. If we look at the depth of 50% of the dose, I'm at 2.2. So in 6 millimeters, I've gone down from 90% of the dose to 50% of the dose. If I want to find R sub P, I track the range of my practical range of my electron beam. I track the tangent line. I track the tangent line of this slope down to the x-axis to see where it intersects. And you can see that it intersects right around 3 centimeters. So 3 centimeters is the practical range of my electron beam for 6E. For the equation is energy divided by 2. So 6 divided by 2 puts me at 3. The majority of the dose after the practical range of the electrons comes from Bremsstrahlung contamination from inside the treatment head of the machine. And you can see at 6E, my Bremsstrahlung tail, my Bremsstrahlung contamination is less than 0.5%. I'm at 0.2%. And this tail is only due to photon contamination of the beam. If we look at isodose lines, Once I start showing you other electron energies, you'll see what happens to these isodose lines, but you have a very rapid fall off. There's a very small clinical range of treatment for 6E, which is why it's not used for much other than superficial skin cancers with maybe a ½ centimeter of bolus. The fall off is just too fast. The risk of using 6E clinically is that you might miss the posterior edge of the tumor. Let's pull in the weighting here and let's assign 100 mu to 9E. You'll notice my isodose lines shifted. Everything shifted deeper. My yellow color here, which is the 90% isodose line, again, which is our clinically treated region in a typical sense, got wider. Let's look at the profile. Okay, look what happened to my surface dose. I'm at 81% for surface dose. My depth of maximum dose is right around 2. My depth of D90 is 2.6. My depth of D80 is 2.9. So I've gone 3 millimeters now for a 10% fall off. The distance from my prescription isodose line of D90 to D50, 2.6 to 3.4. So contrast that to the 6E. If I look at the practical range of the electrons, I take the tangent slope of this, and then I'm intersecting down on the x-axis. Puts me right around 4.5. So 9 divided by 2, 4.5. Anything after the practical range of the electrons is going to be Bremsstrahlung tail. So if you look what happened to my Bremsstrahlung tail, I was at 0.2, now I'm 0.7. So I've tripled, in a relative sense, the amount of Bremsstrahlung photon contamination, although in absolute terms it's still extraordinarily low. If I look at isodose lines, let me flip back and forth here. 6E isodose lines. Watch what happens. 9E isodose lines. Everything's moved down. Everything at the surface is getting slightly hotter. Let's move to 12E. Okay, let me switch one more time. So 9E, 6E, 12E. So let's take a look at the profile. You can start to see what's happening with the shape of the profile now. It's starting to get a much broader range in the shallower distances. So we still have a relative Dmax point. So my surface dose now has increased from 81% to 86%. So you see I'm going up at this 5% increment. So that's why I say these general rules, 75, 80, 85, 90, and 95 for 6E through 20E. I'm increasing to Dmax. My Dmax point at this field is right around 2.8 centimeters, though within a few millimeters around that region I effectively have Dmax. So I'm starting to get a little bit of a broad plateau in the Dmax region. My D90 is 3.7. So my prescription, the physicians typically prescribe at the 90% isodose line, though that's not set in stone. They can prescribe at whatever isodose line they'd like to. I can treat, prescribing at the 90% isodose line, I can treat clinically something 3.7 centimeters deep on the posterior edge. If I prescribe at the 80% isodose line, I can treat something 4 centimeters deep. So my change from D90 to D80 is 10%, and my depth change is 3.7 to 4.1. So I'm able to go 5-ish millimeters in that 10% change. If you contrast that to 6E and remember how fast we fell off, it was only a couple of millimeters. My 50% is 4.8, 4.9, and then for the practical range of the electrons, I'm going to trace this tangent line down okay, to where it's going to intersect the x-axis, and it's going to hit right around 6 centimeters. So the practical range is energy divided by 2, 12 divided by 2 gets me 6. Everything after 6 is predominantly Bremsstrahlung contamination. So you can see now as I follow the Bremsstrahlung tail out, my percentage is at 1.5. So now I'm starting to get into higher photon contamination. 9E was 0.7, now I'm at 1.5, so again I've doubled my Bremsstrahlung contamination. Let's take a look at Isodose lines. You can see what's happening now at higher energies. I'm starting to get this bowing in of my prescription line. My 90% line is starting to bow in, and then my low isodose lines are starting to kind of bow out. Let me go back to 9E so you can see. 6E, 9E, 12E, and let me go to 16E next. So now 90%, you can take a look at the 90% isodose line and see how large it is. And if we take a look at the profile, okay, now you can get a better picture of this broad plateau. So my surface dose, again, has increased 5-ish%. I'm at 91, 92. My Dmax isn't, it's really hard to pinpoint Dmax now. It's a little bit of a range. So it can go probably anywhere from 2 centimeters to 3.5 centimeters. You know, is roughly 100%, you know, or a few tenths of a percent within there. So we have this very large range for Dmax. And D90, my clinically treatable range at 90% is almost 5 centimeters. So if you think my surface dose is at 90%, and if the physician prescribes at the 90% isodose line, you can imagine that 90% isodose line becomes my prescription equals I get total dose, I get total prescription dose at the skin surface. This is where high energy electron fields start to lose their luster, because if I need to use a high energy electron field to penetrate 5 centimeters deep, it's probably not likely that I'm going to have tumor at the skin surface that needs to be treated. So why would I use a high energy electron field to treat something so deep that I still need to have skin sparing, but I'm not going to. And we'll see that for 20E as well. We fry the skin by giving it greater than prescription dose by prescribing at these lower isodose lines. D80 is 5.5 centimeters, R50 6.5 centimeters. If I trace the tangent line down and intersect the x-axis, it hits right around 8 centimeters. And my Bremsstrahlung tail is 3%. So again, I've doubled my Bremsstrahlung contamination at 3%. So I've gone from 0.2 to 0.7 to 1.5 to 3 as I've increased my energy. If I look at isodose lines, again, my D90, my 90% prescription line is going to be my clinical coverage line unless the physician prescribes it something different, like the 95% isodose line, which he or she may in this case because the skin dose is so high. Let me switch back and forth between some of these energies. So this is 16, this is 12, this is 9, this is 6, 9, 12, 16, and now 20. So let me zoom out a little bit. So with 20, if I pull the profile in, I shouldn't say profile, percent depth dose, the skin dose, 93%. Okay, so if we prescribe at even the 95% isodose line, the skin is basically getting full dose. I get this really broad range, you know, from a few centimeters, from 1 centimeter all the way to almost 4 centimeters. I'm getting roughly 98% of the dose. The clinical treatment depth, what we call D90, is 5.5 centimeters. D80s is almost 7 centimeters. R50, or the 50% isodose line, is 8 centimeters. Now if I take the tangent slope, it's a little tough, but if I take the tangent slope down and intersect the x-axis to find my practical range, I'm right around 10 centimeter depth. So 20 divided by 2 is going to give me 10 centimeters, and then everything afterwards here is going to be bremsstrahl contamination, which you can see is at 4%. So with 20E, even after our clinical electron beam has been absorbed by the body and deposited its dose, I still have almost 5% of the dose remaining as bremsstrahl contamination from the treatment head of the machine. As far as isodose lines go, you can see that I'm treating a very, very large region here. I still have dose, I still have 30% dose that's almost 10 centimeters deep within the patient. Let me cycle through. 16, 12, 9, 6. Let me pull the profile, the percent depth doses in, and we'll cycle through. Okay, so you have 6E, 9E, 12E, 16E, 20E, 16, 12, 9, and 6. So let's take a quick look at beam profile for the electron beams. So the red line that's been drawn across here is just another dose profile. So instead of a percent depth dose, it's going to be a beam profile. So the electron fields are flattened to be to give a symmetric and flat beam at Dmax. This is my 6E beam. I have 0 here on the central axis. There's a little bit of aberration here. The algorithm, Electron Monte Carlo algorithm, is going to give these small dosimetric aberrations. That's fine. We can kind of ignore that for the time being. As far as the profile goes, you have the central axis portion here, and then you have what's called the shoulder of the profile, where you kind of get this rounding effect. The penumbra is going to be the 80% isodose line, okay, to 20% isodose line. So the penumbra width for this particular case is going to be negative 7.1 at 80% to negative 8.1 at 20%. So I get a 1 centimeter, distance for penumbra. Again, that's the penumbra is the fuzziness of the beam, and then here I get the tails that trail off at the end, and then I get the same thing on the other side. The goal is to have a flat and symmetric beam around Dmax. So if I do a similar thing for 9E, let me just change this. It's going to look very, very similar. It's just a different beam energy. So again, penumbra goes from 80%, negative 7.2, to 20%, negative 8.3. So again, roughly a 1 centimeter penumbra. So for the same 9E beam, I've drawn another profile at just a slightly deeper depth. So instead of around the Dmax region, 2 centimeters, now I've drawn a profile slightly deeper at 3 centimeters. So I'm roughly at the 80% isodose line. If I look at this profile, so my central axis dose is right around 80. So if I look at the penumbra width, I go 80 times 0.8 is going to be 64. So if I go to 64, my x position distance is going to be negative 6.9. and then 80 times 0.2 for the 20% isodose line is going to be 16. So if I go to 16, I'm at negative 8.6. So instead of having a 1 centimeter penumbra, now my penumbra is 1.7 centimeters. So I have a 70% increase in the size of the penumbra, and that's strictly based on the fact that I'm deeper within the patient. So I have more, as the electron beam travels through the patient, it loses energy. As it's absorbed in the body, 2 MeV per centimeter in water, and then as it loses energy, we have more side scatter, and then the beam kind of spreads out. And you can see this in the isodose lines too. If I put on 20%, and let me turn off everything else. So you can see my distance, my 20 and 80% isodose line is my penumbra thickness. So from here, I'm roughly 8 millimeters is how thick my penumbra is. At the 80% isodose line, this is my penumbra. So now my penumbra is 1.7 centimeters. It's huge. So my penumbra increases as my depth increases, and that's because the electrons lose energy as they travel through the tissues, and then that also increases side scatter. At the end of the day, electron treatments are very useful for superficial treatments, and not necessarily for deep-seated tumors. And again, the reason for that is the higher skin dose with higher energy comes along with the deeper penetration needed to treat those posterior edge of the tumors within the body. So usually in a clinic, you're only going to see electrons used for superficial treatments, or maybe an occasional breast lumpectomy cavity boost, where we're going to use maybe 9 or 12E to boost a lumpectomy cavity for a breast treatment. And the primary reason that we can get away with that is because we're only treating the patient for 5 treatments. Even though there's a higher skin dose than with photon, it's an easy setup for the therapists. You get a fast dose fall off posterior to the lumpectomy cavity, and the high skin dose is mitigated by the fact we're only treating for 5 treatments and not a full course of 30 plus fractions. And that is it for treatment planning examples for electrons.